There we go. Okay, we're recording. So like I said, quick housekeeping note, please keep your questions to the chat window. We'll respond and answer those questions accordingly. Other than the Q&A sections, which we will have, I will unmute everyone and allow for questions at that point. Okay. Let's see, it's about 4 minutes after. All right, so we should be probably a couple of 3 hours into this. It is broken down into 2 sections. We have scheduled it for 4 hours, but I'll probably be giving back some time to everybody on the bridge. I don't think it's going to take that long, but it depends on how many questions and how interactive that we get throughout the session. And a whole bunch of latecomers jumping on right now. I see them. Okay, just real quick, again, housekeeping. Please keep your questions to the chat window, so the group chat. Use the group chat. Chat to everyone on your question, so we can reply back. Patrick, I see, has just joined us. If Patrick, if you don't mind, we'll tabulate those after the fact as well, and we'll get answers to those. Now, during the session, we also have Q&A sections where I'll do an open mic and allow for everybody to ask a question. So I'll just go ahead and mute everybody.
Hey, Doug, one thing.
Yeah,
Patrick.
go ahead, Pat.
It looks like there's 2 in the invite. There was your bridge number and another bridge number. So I'm going to give you host access, so you can have that recorded, and then I'm going to go on the other bridge and let everybody know that this is the proper bridge to go to. Actually, you do have host access, never mind.
Yeah, well, it's my bridge.
Yeah, exactly.
Yeah, this is not WebEx, everybody. We know that, right? Yes. Yeah. No, I'm recording right now, so we should be good. So let's get started.
All right, go ahead.
And I will unmute you, Patrick, just in case you have something to jump on about. If you could just control your mute independently. Same with you, Paul.
Absolutely.
I'll do you too. Okay, so you're both unmuted. So you just control your own mutes. Everybody else is muted out. So, like I said, real quick housekeeping. Keep your questions to the group chat. Paul and Patrick will monitor that, and we'll go through the questions when we get near one of the Q&A sections, and I will unmute as well. All right, so let's get going. So welcome everybody to the basic data primer for data networking, and this is really a networking 101 or a data 101 style course. It's not necessarily related to Business Connect specifically. It's really just a data course, and to understand essentially what we're doing. We're kind of broken down into 2 parts. And we're going to do part 1 today. Part 2 we'll do at a later date. And myself and Rupinder, both of us with Ring Central, we're both the CSEs, Western and Eastern Canada respectively, will be hosting. I will be doing probably the majority of the instruction, but Rupinder, if you're jumped on here so far, just join us and we can go from there. I would like everyone, if we don't mind, if you've got pen and paper, please get something to write things down, because you're going to want to take notes. And also, I have little quizzes and things like that throughout the session, and you'll have to refer back to that when you get near the end of a section or at a Q&A session. So get something out to write. Also, it'd be great to if you've got a dual monitor configuration or a way to check some of the live tests we're going to do, it would be great to have a command window open as well, so you can do some pings and traces and things like that. So we'll get onto that in later part of the section. So the first thing, we want you to write down where you guys stand, where everybody stands as far as knowledge base. So from a data perspective, are you a 0 or are you a 10? Okay, so are you the Einstein of networking? Did you rewrite the data RFCs that would put you at the 10 rating for data? So give yourself a number where you think you are on the data side. And then the same thing on the telephony side. We want to keep this separate. And some people are stronger on telephony, some people are stronger on data. So mark down what you think you are or where you are. And if you were the one that came up with the definition for TDM and know what it means and how it works, maybe you are a 10 on the telephony side. So let's make sure we kind of understand where we are, and we'll reflect on this when we get to the end to see where you've progressed to. So quickly to go over the agenda, we're going to do part 1 today, and I'm thinking it's probably going to take somewhere around the 2-hour mark, and we might be able to get done a little faster. Depends on the number of questions that pop in, and we would love to get it done a little faster. We have booked in 4 hours, so hopefully it doesn't go that bad. With part 1, we're going to kind of start from the bottom up, even though the list is from the top down. It really, just the basics, classifications, and topologies, where we'll go over, kind of the basic functions or basic breakdown of what a network is and how it's built, and then look at the physical connection, the physical actual connection, the hard connection, and then we'll start talking about the OSI model and finish off today's course with OSI and understanding what OSI is. And then touching on part 2 of the course is where we get into kind of the meat and potatoes of the communication, where we move up that OSI model. You'll understand when I say moving up the OSI model. That's a term that's used quite regularly in the data world, and hopefully by the end of this course, you'll understand what that means and how you can interpret it and make it look like you can wear a propeller on your head from that point on. So it's kind of cool. Okay, so the first thing we're going to touch on is classifications, and look at those physical classifications of what topology really means. You'll see a whole bunch of acronyms out in the real world. Typically, you're going to see 2 that are used quite extensively. That's the LAN and the WAN, and local area network is LAN, of course. That is your inside your network. So anything inside your router is considered the LAN or the local area network. And then the WAN is the wide area network or outside your network, typically interconnecting site to site, or you're connecting from city to city, or service provider to an endpoint is considered the WAN or wide area network. And the WAN could be generally considered the internet as well, because the internet is a wide area network. It just connects essentially everybody to everybody, it really in a real standard classification, the internet itself is a network of networks. So you could take a whole bunch of WAN networks and mash them together, and a whole bunch of MAN networks, and something that's not as commonly used, a metropolitan area network. You can mash those all together, and that is the internet. Okay, so you can take all those concepts and use them a little more effectively if you know what they are. The other portions of the network, the PAN, the CAN, and the GAN, you're not going to see very often, and really it's geek speak, and you can kind of impress your friends and relatives, but they're probably not going to know what you're talking about unless they're a geek as well. So we'll concentrate on LAN, WAN, and MAN from this point on. So anytime I refer to a MAN network, you're staying within the confines of a city, and typically you're not going out to a core router that becomes a national network. Okay, a WAN is anything outside your network, whether that's national or it's local. Okay, second part, another quiz we're going to touch on. We're going to look at network topologies and what we consider a network topology. So when somebody asks you, what kind of network you have, what is your topology based on, you're going to go through any one of these definitions and really be able to define what they are. So let's look at, okay, what is the the correct answer for A, and we're looking at, let me turn on my highlighter here real quick. And spotlight, there it is. Okay, so so we're looking at this guy right here, A. Which one would you consider to be A? Everybody write their answer down. And I think that would be called cloud. Yes, correct. Okay, B. If you look through the list, which one does it match the best? Looking at point to point. Very nice. Thank you. Yes, T868277, whoever that might be, answered correctly on that first one. Okay, C. Which one do you think C is? Anybody can answer on the close there, Adam. Very close. Yes, yes, it's a fully meshed network. That is fully meshed. And the definition for fully meshed is every site can talk to every site. That's correct, Jordy. So every site can talk to every site. Okay, let's look at D. Which one do you think D is out of the list of the remaining answers? Very good. Oh yeah, all the right answers are popping in. Fantastic. Yes, that's a bus network. And we look at E. Anybody got that one? Yes, that's a star network. Very good. Good answer, Mustafa. Tanvir, correct. Jay Fernandez, correct. Everybody's correct. F. What do you think this one is? This is the one you stay out of. Right on, Jordy. Yes, that's a mess. Stay away from that. You don't want to be touching that. Thanks, Brendan. Yes, correct. And 2 more to go. Okay, so G. I think we touched on this one already. Yes, partial mesh, and that is correct because you may have to go through another site to get to a site. In this example, if this site here wanted to touch on this site or connect to it directly, they would have to go through an intermediary site, okay, to route to it, okay. It's the only way to get there, so that would be a partial mesh. And the last one, it's pretty evident. We only have one left. It's a star bus. Fantastic. I hope everybody got the correct answers through that. It looked like through the chat we had that almost 100%. So that's fantastic. Now, in the next section, the communication modes where those networks really talk are the devices that have to talk to each other. And in certain situations, you're going to have a master-slave relationship. You're going to have a peer-to-peer relationship or a client-server relationship. And they all have different definitions of how they communicate, and there are more models of how this communication can occur. But typically, a master-slave is where you have a master that makes the decisions and does the processing, and the slave is conducting its instructions towards it, or adds data or removes data from that link. A peer-to-peer is typically a machine-to-machine direct connection, kind of a 50-50 split in how those devices are connected. Peer-to-peer networks happen very commonly in the world nowadays with torrents, and you will see that in a file sharing network where you have a peer-to-peer relationship. In a client-server relationship, this is really important in client-server relationship, where you're essentially doing a screen scrape or a hyper client that sits on top of a machine that runs as a small application that's talking to a server, and that server does 99% of what is required from a compute standpoint. And the client is essentially just directing the server to do something, and the server sends back its results to show you that that service has been completed. Thin clients, for example, is a client-server environment. Citrix, that's typically what you'll see. In a network signaling standpoint, we're going to touch on a couple of modes and just go through what they are, just to understand them. You may or may not have any reference or use for these, but one that's very particular to us is FDM, or what they call frequency division multiplexing. And FDM allows for signals to be transmitted in a busy environment to eliminate crosstalk or cross interference between those two channels or frequencies. And the way that's done with FM is a frequency modulation, where the frequency is actually squashed and then spread out and then squashed and spread out, and you'll see that frequency go up and down. That is the mathematical calculation that's done to make that happen. is the input frequency. The signal that we're sending is causing that frequency modulation in an FM band. Typically, FM is a very quiet network. There's not a lot of noise because you're not hitting that 0 point in between. FM radio, as you know, has very, very good audio quality, and that's the reason why is because of that modulated signal of how it's operated. Okay. In an AM world or amplitude modulation, you'll notice that AM radios are always noisy, and there's never really, that real high quality or high fidelity information that is passed through from the endpoints. And typically, because if you look at this waveform, you'll see that waveform that's the sinusoidal waveform that is the signal. Okay, the blue line, and that's in all examples, is the carrier wave or the carrier frequency, and you'll hear that term carrier frequency and then signals frequency, and they interoperate with each other to form a modulated signal, and that's what amplitude modulation does. FM is the same thing. The next one is phase modulation. You're not going to see this very often. Typically, it's used with satellite communications. And it's the telemetry portion that's used, or the signal that is your uplink or downlink towards a satellite. They use phase modulation. It's not used in a lot of public consumption. And then the two bottom ones are methods to kind of increase the bandwidth of that signaling characteristic to get more data or more defined analog to digital conversion, where we use a amplitude shift keying. Where you can actually hit hard high or low, okay, depending on where that signal is, which is a 1 or a 0. Infrared remotes use amplitude keying. Fiber optics use the same sort of thing to communicate end to end, and you can get high bandwidth, high bit rates through ASK, and finally FSK. FSK is typically used in modems for analog communication. That is passing digital information, and it's essentially squashing that waveform to give a high or a low, or a 1 or a 0, where rather than a amplitude or a signal that varies up and down like AM or FM. Okay, you have a varying frequency signal in both of these, and PM as well. ASK and FSK are going to give you a hard 1 or a 0 to give you a data communication. And all of these are really measured in, typically measured in hertz, kilohertz, megahertz, gigahertz, and the carrier frequency, signal frequency, is what we're referring to in that form. Now, the next one that we're going to talk about is TDM, or time division multiplexing. This is one that is very, very common in our world in communications, and the reason why is because it was born around the whole T1, DS1, DS3 technology that allows for multiplexing or multiple sources to use the same wire or the same signal, and it will utilize that time slot to be able to separate communication streams. And time slot 1 would be designated to source 1, so that is the source that is going to use that time slot. Time slot 2 is being used by source 2, and time slot 3 is being used by source 3, all with different data characteristics or different data information that it's passing. Because this clock is moving so fast around, it looks like an instantaneous communication. It's not instantaneous. It does give time slots, but those time slots are imperceptual to human beings. We can't really see that because it's traveling so fast. Machines certainly can, but they don't worry about it because they can always wait and listen for more data, and they're processing information at the same time, so they need a little bit extra time. Now that signaling, it translates to a transmission medium, and ways that the transmission mediums talk to each other are a number of different methods. Simplex communication is simply that. It's simple. It's one way, and it would be very much like you talking to your pet. Typically, you're not going to get a response, not qualifying barking as a response, but it's simplex. It's one-way communication. You're telling your dog to sit, and it's ignoring you. There's a packet loss, that type of thing. If your dog sits when you say sit, then transmission successful. That type of thing. There is no response from that device or machine in the simplex world. In half duplex, the easiest analogy to understand half duplex is a two-way radio. Okay, a CB radio. Everybody's probably used a CB radio or a radio of some sort where only one person can talk at a time. In the data world, this is very, very common in what they call a hub, not a switch, but a hub. Anytime you ask somebody, do they have hubs in their network? That's where you have to kind of put your ear to the wall and start listening to what that person is really saying. Because anytime they say yes to a hub, they've got a half duplex situation, and that wreaks havoc for voice communication. So we want to stay away from that. Full duplex is where we typically play and we want to play, because everybody can talk at the same time, and allows for bidirectional communication back and forth. And it's done so fast that it looks seamless and very little collision. There's methods of how this is accomplished through the signaling schema of the device that's doing it, but we're trying to keep this a little simpler. We won't go into that detail. That could be another course in itself on how duplex works. But one of the situations that we run into a lot in data communication world is half duplex, full duplex mismatch. And you will talk to a device, and when I say you, I mean a device, a switch or a router, will want to talk to another device in a given method, whether that's half duplex or full duplex. The default is half duplex because it's simpler. Full duplex allows for that bidirectional communication. Yes, it wants to do that, but it has to be hard coded. So when you're having an issue with, yes, you have connectivity. Yes, you can make a connection between two machines, whether that's a ping or a trace, but it's not stable. Okay, and you see bandwidth in an asymmetrical format, so you're getting more down bandwidth than up bandwidth, or vice versa, and it's significantly different. Or there's a definitely amount of bandwidth that seems to be missing. You're on a 100 meg network, and you can only get 10 meg or 5 meg out of it. There's likely either, if it's not a hardware fault, a bad cable or a bad port or bad piece of routing equipment, it's more than likely a half full duplex mismatch. And that's where one device is trying to talk at half duplex and another device is trying to talk at full duplex. And what this will seem like is, or what it will be evident, is the full duplex device will have all of its ports manually set to 100 meg full, and there would be one device sitting in the network, whether it's a switch or a hub, and it'll be set to auto. Okay, and because it doesn't talk at auto to a fixed connection, the device that's sitting on auto will downgrade itself to the lowest common denominator, which happens to be 10 meg half duplex. And when it's sitting there trying to talk to 100 meg full, you get all kinds of communication errors between the two of them. Okay. Now, the other two forms of transmission, synchronous and asynchronous, this is something that seems to get misplaced or misspoken. People talk about DSL or a modem of some sort, like a cable modem, or DSL, a home network. I have a 50 meg asynchronous connection. Well, no, you don't. It's probably an asymmetrical is what you're talking about, not asynchronous. Asynchronous refers to timing, being the root of the word is chronos. Okay, as you can see, chronos here, synchronous means that both parties are listening to a clock, and they're right in step with each other, so they can listen and communicate to a clock. Asynchronous is start and stop. Okay, there's no constant clock. Probably the best analogy would be synchronous. You're face to face. You're talking to somebody, and you're making communication happen by saying words, and the other person listens. That person talks, and you listen. That's synchronous. It's real time. Asynchronous is that start and stop. You write them a letter. You leave it on their door. Okay, and they come back home. They see the note. They read the note. Okay, they write a note and they send it. Best example of asynchronous communication would be a chess game played online, okay, over time. You know, you make a move, you let the person know what that move is. The next day, the person comes back, looks at that move, makes another move, and sends back a response. That would be asynchronous communication. Okay. Now, symmetrical and asymmetrical is when we talk bandwidth. Symmetrical bandwidth is equal bandwidth towards the network and away from the network, or up and down. So if you have a 10 meg symmetrical network, that means that the network can transmit and receive at 10 megabits per second. Okay, not 10 megabytes, but 10 megabits per second. An asymmetrical connection would be exactly that, not symmetrical or asymmetrical. So more bandwidth in one direction. 99% of what you're going to see in the real world when it comes to DSL or cable modems will be asymmetrical. You'll be paying, say, to TELUS for a 25.5. That's asymmetrical because it's not symmetric. You have 25 meg down towards the network, and you have 5 megs up towards TELUS. Okay, that's asymmetrical. Same thing with Shaw on their 150 package. They get 150 down and 20 up, or 150 down and 15 up. That would be asymmetrical. Now, in the TELUS world, the fiber, the 150 fiber that you can buy, that they say it's 150 down, 150 up, that's symmetrical. Okay, so it's a symmetric connection, it's pretty evident when you start using it, the difference in performance. Because probably the biggest thing that I'd like to really get everybody to understand is bandwidth in a network is not really speed. Okay, and it's kind of a misnomer out there that everybody thinks that the more bandwidth you've got is the more speed you have. Well, it's not really that. That's not really it. In technical terms, it's bandwidth is the amount of how big that pipe is. The speed is constant. Okay, essentially data communication runs near the speed of light, and that's constant. Okay, as we know, E equals mc squared. That c constant is the speed of light, and it's 180,000 miles per second or meters per second, and that is something that it doesn't change. It's the amount of bandwidth that you can, the amount of data that you can get from one point to the other is the size of that pipe. The best analogy for bandwidth is a garden hose versus a fire hydrant. Okay, and that's your bandwidth, because you've got a garden hose at a 1/2 inch, okay, or a 3/4 inch garden hose, and you've got a fire hydrant that might be a 4-inch pipe, okay, an enormous amount of water. It's still coming through at the same speed, but you just get a lot more of it in a shorter period of time. It gives you the perception of speed, but it's not really any faster. It's the same speed. It's something that a pet peeve of mine when people say they need more speed. No, they just need a bigger pipe. Unfortunately, Shaw came up with the best company name in the internet when they came up with their big pipe company name when they were selling business data communications. They called it Big Pipe, and that's exactly what they were selling. It's not speed. Now, broadband versus baseband, and this kind of follows into that a little bit. A broadband essentially allowing for multiple signals on that same wire, and you kind of feed off what you want to get off that signal. The best analogy is cable TV. Being able to listen to one piece of frequency out of a very wide range of frequencies. You're tuning to that particular frequency, and that's really the where broadband comes from. Baseband is a single wire, and what we talk about in the data communication world is baseband. So 10 meg, 100 meg, you know, 1,000 meg is what we call a baseband connection, and you know, that's where we get that 10 base T, 100 base T, or 1,000 base T is the proper name for that connection. And Ethernet is that 10 base T, you know, 100 base T. Back in 20 years ago, that's what it was referred to. It wasn't called Ethernet, it was called 100 base T. You know, if you wanted to be a geek, you could say, oh yeah, 100 base T or 100 FXT or whatever it might be at the point, whether it was Ethernet or it was cable modem or it was coax. There was different names, but we're going to concentrate on Ethernet because that's the way of the world nowadays. So I'll open up the microphone now for the group. So I'll unmute everybody. If we have any questions on classifications, physical classifications, we can pose them now. I don't see anything that came in on the chat window. All quiet. That's good. Okay, fantastic. We'll move on.
Just took a packet for Tim as well before I even reset the field interface.
Okay, I don't think there was a question there, so I'll mute on. There we go. Okay, next section we'll talk about is the physical connections and what we do in the real world when we need to have a physical connection from one machine to another, or a machine to a network, or a network to a network, and we'll go into explanations of what those physically are and how they operate. Now, when a physical connection happens, you typically are going to use a twisted pair cable, and that twisted pair cable is defined in a number of different forms. UTP is very simply unshielded twisted pair. And STP, guess what, is shielded twisted pair. That's the two classifications essentially that covers 99% of the cables that you'll see out there, whether it's a coax cable, well, it's a single conductor, but it would be the shielded or unshielded, and typically we're looking at twisted pair cable that's running an Ethernet connection. Now, physically, the cables will be sheathed or covered with a particular material in what we call a plenum grade or Teflon. They're essentially it's fire rated, what we call FT6, and that Teflon coated cable can run between floors in an office building because it doesn't stay on fire. It puts itself out. That's the biggest reason why they call it plenum cable, because it can run in open ceilings. And be aware if you're getting a cabling job done and it does run between floors in a ceiling, certain building codes will stipulate that the cable, if it has to transmit or physically transit between two buildings through a fire stop, they must be plenum rated cable. Okay, and that's what we call Teflon cable. It's a rather hard connection or hard cable, easy to use, but they're prone to kinking quite readily. The one that's most common, probably 90% of the cable you see, is polyvinyl chloride, and that's PVC is a common name for PVC. FT4 is the technical term used, or the technical designation used for polyvinyl chloride, and that is most of the cable you will see. It's a much softer cable and allows for bending and putting into bundles. It's much easier to handle. And typically comes with a strip string inside that physical cable to strip that cable back, or the sheath back, with the twisted pair inside it. And those are the two. A USB or universal serial bus cable is essentially twisted pair cable inside a shielded case, and that shielded case will have either a fiber or a fiber material like a cloth or semi-synthetic, and then covered with a rubber or some other material on the outside. If you ever cut open a USB cable, you'll see that they're just copper wires inside. Nothing special. And the same thing with firewire cabling. It looks very similar. The IEEE 1394, which is the actual name, FireWire, is what Apple pays for and uses. So I should have the little trademark symbol beside FireWire, but IEEE 1394 is the proper name for a FireWire cable. Now, when I've mentioned before, machines talking to machines, or a machine talking to a router or an endpoint. So it's computer to computer, computer to a router, or router to a router. That's what we refer to in the world of DTE versus DCE. It's a very old term. It harkens back to the day when we had serial communication and all we had was modems and add drop units and T1 multiplexers and all that fun stuff way back. And you had to be really concerned about, okay, is the device I'm talking to, is it a DTE device or is it a DCE device? And everybody's kind of scratching your head. What do you mean by that? Well, the DCE device is a data communication or circuit terminating equipment. So any communication equipment, hub, switch, CSU, DSU, a modem, is a communication equipment, DCE, okay? And a DTE device is a termination equipment, data termination equipment, which is your computer, your router, your IP phone would be considered a DTE device. And there's logic that's implied by using this term that's very important to understand, and that it comes down to cabling logic and making sure that we communicate correctly between those two devices, or actually make a connection between those two devices that will actually work. So when you have two devices that need to talk to each other, you have to determine the correct cable that goes between them. So a DCE to DCE device versus DCE to DTE device. Okay, you're probably not going to hear these terms very commonly, but they're used as a reference to understand: is this a switch? Is it a CSU? Is it a modem? Or is it a computer or a router? You notice that a router is a DTE and a DCE is a switch. Okay, and you'll understand in a little bit what that means. In the world of cabling, you essentially we conform to a TIA or EIA standard, which is the 568A and B in the Ethernet world, and that's this number here, EIA 568A and 568B. So in that wiring world, that determines what wires appear on what pins on an RJ45 connector, okay? And that RJ45 connector will have all 8 of those wires, even though we only use 4 of them. 2 for transmit and 2 for receive, but they still have to be in a specific order to be able to communicate end to end. Now imagine if I'm a DTE device and I have my transmit sending out on pins 3 and 6, okay, the orange pair. Well, at the other end of the communication, the receive side is receiving on pins 1 and 2. Okay, its transmit would be on 3 and 4 as well. So if it's DTE to DTE or DCE to DCE, then we have to use what we call a crossover cable. So we take that transmit pin and we send it to the receive side, and we take the receive side and send it to the transmit side. Okay, so they cross over. If in the world of DTE to DTC, or sorry, DTE to DCE, you have a fixed transmit pin, receive pin, and they are always opposite each other, okay? So in the world where you're talking, your transmit is on 3 and 6, and your receive on the other piece of equipment is on 3 and 6, straight through cable. Perfectly works, okay? This is most of your connection is in the world of this, in this realm, okay? And that's the DTE to DCE, okay? When you have to talk and this A to A or B to B standard is telling you, is it an A connection on one end or is it a B connection on the other end? Okay, as long as it's A on one end and A on the other end, or B on one end and B on the other end, that's a straight through cable. Okay, you'll notice that the cables here, we have the white green on 1 and 2, and on a B connection, that white green cable is on 3 and 6. Okay, I don't know if that's clear to everybody, but that's on 3 and 6. So that's the difference. The orange, the other pairs never move. Okay, the white blue pair and the white brown pair never move. Now the white orange pair on B is on 1 and 2. but on the A side, it's on 3 and 6. So if you elect to use 568A wiring or 568B wiring, as long as you're using it on both ends, you have a straight through cable. It's when you take the A and you send it to a B end, A to B, that's when we start getting cross wiring, okay, or what we call a crossover cable. And that crossover cable allows for like machines to talk to each other, DTE to DTE, or DCE to DCE. And on the previous slide, as you remember, that would be a switch talking to a switch, okay, a computer talking to a computer, okay, a router to a router. But if it's a router to a switch, that's a straight through cable. Okay, so anything that communicates inside this piece of this arena, okay, the DTE world, you need a crossover cable. Anything that talks in this to this, you need a crossover cable. The second you go from here to here, it's straight through. And this is the majority of what we'll see, okay? It's a switch to a router. It's a switch to a computer, okay? You want to connect a computer directly to a router, you need a crossover cable, okay? Because they're both TTE devices. That's why that logic is in place. I hope that's clear, everybody. I don't see any questions popping in on the group chat. That's great. I just want to make sure that that logic is followed through. You'll see this a lot in wiring closets. It doesn't matter whether an entire company elects to go 568A or B, as long as it's the same on both ends. It's only when you crisscross, you go A to B or B to A, that's when you have a crossover cable or crossover situation. So it's very easy to determine when you look at a cabling connector, RJ48 in this example, or RJ45, and you look at the colors through that connector. Okay, you will see the color pattern of that connector, and it's very evident when you look at the green pair is on pins 1 and 2. It doesn't matter if it's on left or right. It'll always be opposite the brown pair. Okay, so you have the white green pair and the white brown pair. And you look at the other end of the cable, and you see that it's white green pair and white brown pair on the same pins. That's a straight through cable. It's when you see this crossover, that's when they change. Okay, now on the connectors themselves, you will see differences in RJ numbers, and those RJ numbers are really a registered jack is what RJ stands for, by the way. And there's RP connectors as well. That's registered plug. We don't even get into plugs, but RJ is where we live in this world. Everybody probably wondered what RJ stands for. It's certainly not a backwards FM station in Vancouver. It's it's not JRFM. It's RJFM. The RJ45 is 99% of what we're going to see in the world of communications, and that's the 8-wire Ethernet cabling connector. That's this guy at the bottom here. It has 8 pins and is wired a specific way to give you that data connection. On the previous slide is what I described. The RJ48 is exactly the same connector, but it's just used for a different function, PRIs and T1s, okay? And it could be wired slightly differently, but typically transmit and receive are still in the same pins, okay? But it's probably only gonna be a 4-wire connection into that. And a lot of the time the technicians will build an RJ48 connector. And there's different variants. There's RJ48X, RJ48C. I won't get into that, but there's different ways of using this, okay? A question from Brandon, I just noticed popped on. He's asking, had an installer tell me the pattern for straight through was brown, green, blue, orange, left to right, but on the diagram it shows slightly different. To be honest with you, it really depends on the installer. But if you look at any commercial cable, and I literally mean any commercial cable that you buy from a store, even a dollar store, that wiring standard will always follow the EIA 568 standard, whether it's A or B. Okay, so when you look at a cable, you will see the blue pair is always in the middle, always 4-5, always on the center 2 pins, and it's always straddled by the orange pair. Okay, if it's a B cable, it'll be straddled by the green pair, but typically it's blue and then straddled by a pair, and then the green is by itself and brown is by itself. This is 100% of the world. No, he's probably not incorrect, Brandon, but is certainly if whoever the technician is. If they did this backwards, if the other end is done the exact same way, then it's still considered, you know, a straight through cable. Okay, it may not be exactly to standard, but it's still a straight through cable. Okay. So really the colors are what the standard specifies, but if a technician wants to deviate from that, as long as you do the same thing at the other end, you're good to go. Okay, makes it a bit of a nightmare for the next technician to come in and try to troubleshoot something, so that's why you want to stick to a standard, right? Yeah, absolutely. Thank you, Eric. That's exactly right. Some people make their own cables, and yeah, just look at both ends to see if it's straight through. If you see a difference, it's going to be a crossover. Exactly right. Okay, so in the fiber optic world, we have a little different communication standards, and two of those standards that are used are single mode and multi-mode. Single mode typically is going to be used for long haul, and that's the best analogy is the rifle. Okay, it's a pinpoint accurate shot. From one end to another. It uses very small physical medium. The size of the glass or the plastic inside that cable is very, very tiny, and it pushes it very, very long distances. Of course, it's typically 99% of the time a single mode is going to be laser. Okay, and laser light. Do not ever look into the end of a cable coming out of the wall, you know, those yellow cables. Don't ever look into them because it can burn the back of your retina in mere seconds. Okay, and yes, sorry, let me step back. Related to a computer to router connections requiring the crossover cable, what situation is that actually necessary? Because we can obviously run a regular A or B cable from a router to a computer without any issues. Yes, that's correct. So Jordy, that question, the only time you use a crossover cable is when you have two computers side by side and you want to communicate directly, and you have no switch, you have no router, okay? You just want to statically assign an IP address on both machines, and you want to plug a cable between the two. A straight through cable will not work. You have to have a crossover because both of them are DTEs. Okay, going back to our DTE, DCE discussion. Okay, hopefully that answers your question, Jordy. Yes, that is correct. Yes, if you're going to plug a computer directly into a router, that router now that raises a really good question, and probably something that a lot of people will see. Yeah, that's a great question, Jordy. You'll see router and computer are on the same page, right? But switch is on the other one. Okay, in our world, and I failed to put this in here, and thank you for highlighting that. We see a lot of combination devices, okay? And I mean probably nearly 100% of the devices that we deal with on a day-to-day basis are combination devices. Your D-Links, your Linksys, your Asus, all these different manufacturers have routers that they sell as routers that you plug into your home network, okay? Those are combination devices. They're not dedicated router. When you talk about a router as a DTE piece of equipment, I'm talking a Cisco 3500, okay, or a Juniper, okay. The enterprise class router that all it is a layer 3 device, that router is a DTE. It does not have switch ports. Okay, switch ports on a switch are integrated into a Linksys, home use router, or even a small business router will have switch ports built into it. They are DCE devices, so they do that switch internally between the switch section and the router section in software. Okay, hopefully that makes sense. Perfect, thank you. Okay, so combination devices, we see that a lot between switch and router. When you break it down, say you have an HP switch, a Cisco 2960 as your aggregation layer, and we're getting into a totally different course in a design course, but you get a switch layer where all your PCs connect into, and then that switch connects into a Cisco router. That's all straight through cables because they're all DCE to DTE, DTE to DCE devices, right? It's when you're going from a switch to a switch, you're using a a cascade cable, okay, between two switches. If the switch port does not have auto negotiate built in or auto sense, and that's another total different course, and it probably raises a really good question, is two Cisco switches that you plug a straight through cable in will work. And the reason why is because they have what they call auto negotiation. They switch their pins automatically inside once they sense that connection. Okay, I'm connected to another switch. Oh, make me a DCE, make me a DTE. Boom, they start talking. Okay, in the traditional world where it's fixed, and in our data world, we really want to make sure that connections stay what they're supposed to stay. I'm not a big fan of auto setting of any kind. I like to have a static setting. Other than DHCP, again, a totally different conversation, but I like to have a static connection. So a physical connection between two devices. I'm going to say I'm going to talk at 100 meg, and I'm going to be a DCE device. I'm a router, I'm a switch, and I want to talk to another switch. Okay, I'm going to make that a auto neg connection because I need that to connect together. But I want to force them to 100 meg full duplex, and one is a DCE and one is the DTE, okay, that auto negotiation part. And I will use a crossover cable between the two of them. I hope that makes sense. Okay, so a crossover cable physically between the two, and both forced at 100 meg full duplex. No auto settings whatsoever at all. Okay, and that's the world I like to live in. DHCP at the software level, layer 3, that's a different conversation completely. Okay, and you run into less problems when you're configuring network devices when you know that a physical device is stuck or forced into a particular mode. Okay. Okay, perfect. Okay, and it looks like that's all the questions that came through. Perfect. Thank you very much. Okay, so that covers the cabling logic and the connectors that we talked about, and let's finish off with the fiber optics. So, like I mentioned, single mode is that long haul connection, and I can't warn you enough. I've already mentioned it. Do not look into the end of a fiber optic cable to see if the light is on. Yes, you will see it, but it will burn out your retina, and it has happened. They have special glasses. People that do this for a living. You'll see the splicing trucks on the side of the road, and they'll have a big loop of cable. Typically, they're beside a railway track or something, and they'll have a big loop of cable in the back of the truck, and they're doing a physical splice, whether it's a fusion splice or a hot splice or it's a butt splice, which is a cold splice. They will physically have glasses on, special glasses to filter that laser light. Okay, so it makes it safer for them, because even a flash from it, like you don't want to look in the end of a high-powered laser pointer, because that's the kind of power that we're talking about. They're in milliwatts, okay, to drive this data signal from end to end. Multi-mode, not so much, because they're typically LEDs as their light source, but the disadvantage with LEDs, because they're a lot lower in power level, they don't travel anywhere near as far, and multi-mode also uses a different cabling standard. So the fiber optic itself, the glass or the filament that you see, the plastic filament inside the cable, is much larger, and there's a whole course on just from fiber optics and to do with boundary layers and reflection off the inside and refraction off that glass. I'm not even going to go into that, but there's a whole new course another course on fiber optics that goes into the design and how it's transmitted and what losses are and things like that. But that's fiber optics. Now in the Wi-Fi world, oh my God, the things that we go through in Wi-Fi and the standards that are out there, just the standards alone under 802.11, whatever, can just, it's a nightmare, okay, as far as a data communication network. There's so much of it. If you ever get the chance, there's no reason to, grab your Android or Apple phone and load up a Wi-Fi analyzer, okay? You can download them for free from nearly anywhere. Those Wi-Fi analyzers, you will be absolutely amazed how many networks you see, and our airwaves are just flooded, and I mean flooded with networks, and they're always talking, especially in an apartment building or in a office tower. You turn on a Wi-Fi analyzer, and you will see, even if you just touch on your own computer, look for networks from your the sys tray on the bottom right of your screen, you will see a whole bunch of Wi-Fi networks that are available to join. In a mall, it's insane how many are out there. And they're all operating in between, with each other. Probably the biggest thing that I can tell you about Wi-Fi is that it is not full duplex. Okay, it is half duplex communication. Radio communication is half duplex. There is not a dedicated band for transmit and receive. They are transmitting and receiving on the same band or same frequencies. So what happens is that communication will use an enormous amount of bandwidth. The pipe is enormous to try to get through as much data as possible in the shortest period of time, and then respond back with that in their time slot with a response to give you the impression that it's running at a very high speed. When you look at things like 802.11n, okay, they rate that at 600 meg. This is absolutely perfect conditions when your computer is sitting 2 feet away from the wireless router, and remember, your bandwidth is inversely proportional to distance, and that's essentially every 10 feet you go away from a router, that wireless connection speed performance will drop by half. And if you go 10 feet again, it'll drop by half again, and it will drop off to the point where you barely have any bandwidth at all to that end device. And you can try it very easily to look at your Windows Wi-Fi connection and go to the status. It will show you the speed that it's communicating at, or the bandwidth that's available at that particular range. As you walk away, that number will drop very, very fast. As you walk towards the router, and it will ramp up very, very fast. You will typically never get, even close to 150 or 200 meg on a wireless network. I don't care how well it's engineered, unless you're sitting right on top of the router and there's nobody else in the network, because everybody's competing for that bandwidth. Okay, and I mean everybody's competing for that bandwidth if it's on the same SSID. So this is very confusing. This could be a course all on its own as well in Wi-Fi. Probably the biggest learning point is if you're going to use Wi-Fi network for voice over IP communication, it better be put together correctly. Okay, things like 802.11e, okay, QoS for voice over wireless. Okay, this has to be considered. You have to look at QoS on Wi-Fi to be able to prioritize those packets. Yes, Mustafa, exactly. 600 meg is really hard to achieve and impossible in the real world. Yep, absolutely. Totally agree with you. And that's kind of my point. Is it's marketing. I hate to say marketing wank, but that's what it is. Yes, it's tested in a lab when the technician is sitting right beside a router, and sure, he connects at 600 meg. But he moves the machine half a foot away and it drops. Yeah, it's ridiculous. But getting back to voice over IP, if you're going to put devices on the network that are going to run voice over IP, minimize them. Have as few as possible, and I mean as few as possible. Try to stay away from Wi-Fi enabled phones. Okay, if you've got Wi-Fi enabled phones and you don't have any choice, keep them to a minimum. Okay, if anything, set them up on a separate SSID if you can do that. Get them off of the network that everybody else is connecting to, because like I said, everything is sharing that bandwidth, and it can be an absolute nightmare to manage. And that bandwidth is also being shared by things like baby monitors, microwave ovens. They can cause all kinds of interference. The best thing you can do is to get there's a program for Windows and Mac, and it's called Insider, and that's spelt with SSID inside it. So it's INSSID-er, so Insider. You might want to write that down, INSSID-ER. And that piece of software you can run on a Macintosh or a PC. There's free versions of it. There's paid versions, of course, but the free version is fantastic because then you see what networks are out there, what's available, what frequencies, what kind of channel interference you've seen. Interchannel interference is that could be a course on its own as well. To design a proper Wi-Fi network, to make sure you don't have cross-channel interference, and your own dedicated bandwidth, because it's all shared media. You know, the wavelength that you see flying through the air at 2.4 gig or 5 gig is all shared with everything. Okay, I don't want to go into that too deeply because we can run off to Never Never Land talking about Wi-Fi. Okay, physical connection Q&A time. I will unmute. There we go. And do we have any questions or discussion on the Q&A for physical connections? We covered a lot of it already.
And some characters.
It's a big guy, the kids go crazy, like my nephew.
Okay.
He's public school.
Sounds like we got a couple other conversations going on at the same time. That's cool. Okay, I'm just going to mute out. If you have any questions, just pop them on the group chat. That'd be appreciated. Thank you very much. Okay, now we're going to get into a little bit more complicated stuff, and I'm going to refer to stuff that you may not ever use in your life again. But to understand the OSI model, it really is really what you need to understand when it comes to data communication, because data communication is one of the hardest things you can possibly troubleshoot, because that communication is all unseen. You can't physically see it. Okay, it's not like trying to figure out, okay, where's that leak coming from? Is my hot water tank leaking? I see a drip. There's a puddle. Oh, there's a problem. Okay, in the data world, you don't see those leaks. Okay, you don't see those transmission failures. It's always something is happening that is not normal. Somebody says, well, I'm not getting this communication, or I'm not getting this connection, or I can't connect to a particular application or device, and that's where your troubleshooting skills have to come in. And understanding the OSI model is paramount to be able to troubleshoot. I don't want to scare anybody with the 7-layer dip that I've got on the screen, but to be honest with you, not every piece of gear or every application or every device uses every single layer. A lot of them can be skipped, or a few of them can be skipped. But the ones that we will talk about in data networking are really the 3 bottom ones. Okay, layer 1, layer 2, and layer 3. Okay, everything else is essentially, it's application driven or device driven. Above that, the application and the users are kind of, you know, essential. Without them, you can't have the rest. But again, at the bottom, the physical layer, the data link layer, and the network layer, what we call layer 1, layer 2, and layer 3. I will frequently, you know, in conversation with a lot of you individuals, saying, you know, what do you have for layer 2 devices in your network? Well, what do you think that means? Well, that's data link layer. Those are switches. Okay, those are layer 2 devices inside there. And then, well, what's your layer 3 routing? Well, that's your router. That's your network layer. Okay, that's all important. That's where IP happens inside the network. Okay, very, very important. Just understanding this, it makes it much easier to understand what's happening in your network. To remember, if you're interested, to remember the OSI mnemonics. All people seem to need data processing. Okay, so you have the application layer, the presentation layer, the session layer, the transmission or transport layer, the network layer, data link, and physical. Okay, so that's from top to bottom. From bottom up, please do not tell salespeople anything. That's the one I love the best, because it goes from your physical layer to your data link, your network, your transport, your session, your presentation, and your application. Okay, it's a nice, easy way to kind of remember the layers. Again, this is geek speak. It's great to impress your buddies, you know, with a beer at the bar or wherever you're doing it, and you know, it's kind of cool. Now, the best analogy I've got to explain OSI is a post office, and this really rings true for the most part. You know, physically you have to move material from one point to another, and that physical layer essentially is that, you know, it's that transport, the truck, whether it's an airplane or it's a, you know, it's a truck or an airplane or a rail car or something, physically has to move from one location to another. That's your physical layer, and that's referred to layer one. That is your physical medium, whether it's copper and using electrical signals, or it's fiber optic and using optical or light signals, or it's a radio link and it's using radio waves or RF. That's your physical layer. Now, the data link is your envelope. And the one thing I want you guys to get out of this once we get down to the bottom is encapsulation. Okay, remember that term, encapsulation, because once you understand that, the OSI model makes really a lot of sense. And what we're taking is the data that contains at the bottom of this screen. It should be the other way around with the application, you know, sending it down to the physical layer, is encapsulating. We're de-encapsulating. We're taking data out of this link. So we take the letter out of the truck. That's the data link layer. And we have to process it with the network. That's the address information. Where is it going? Okay. You know, once it's going, okay, what application is going to use this? That's our transport, the name on the envelope. Okay, that's the application. And then, okay, what format are we going to talk? That's the session or the letter format. And then, okay, the body itself, that's considered the translation from different languages. EBCDIC to ASCII, for example, is a good analogy or good representation of what presentation layer is. It's typically skipped in a lot of environment. And then of course it's the application. What are we doing with it? Okay, when it's finally out. And yeah, we're going to read a document. Okay, and I think that's a rather famous person reading a document there. And now we'll kind of go through from these different layers what they're physically doing and what they are. The physical layer, or layer one in the OSI model, deals with the ones and zeros. And if you remember back to our FDM, frequency division multiplexing, and TDM, time division multiplexing, way back in a slide earlier, we talked about highs and lows, high frequency, low frequencies, ones and zeros. That's the physical medium that we want to, or the physical information that we want to transmit on that media. And it can be a high electrical signal, being a 1, or a 0, or a low electrical signal, which is a 0, or in the fiber optic world, the light's on or the light's off, okay? Or the light's off and the light's on. I think that's the one is on, one is off in this example, okay? The medium that's used, or the media, copper, fiber, wireless. Sonnet is typically, well, is a physical layer, and it's going to be a serial communication, that T carrier or E carrier in Europe. So T1s, T3s, that type of thing, or DS1s, DS3s, your carrier, and that refers or is explained more, references bandwidth and the channel type, okay, and whether it's TDM or even you know, quantization division multiplexing, which is another topic. And repeaters, or hubs, typically are considered physical layer devices as well. You know, multi-port repeaters, media converters, CSU, DSUs, modems, RS-232 is an example. These are all specifications for that physical layer. And hubs really are a physical layer device because they don't really speak anything. They speak electrical, ones and zeros, different than a switch, and that's why we kind of stay away from hubs, because they're rather brainless. Oh, sorry, Brandon. Did I say that bandwidth said the speed? I probably misspoke. Yeah, you caught me. Thank you. Yeah, I should fix that. Yeah. Speeds, bandwidth. Yeah, you're right. Absolutely. Bandwidth is, yeah, how big that pipe is. Yeah, how much data can we get through in a given period of time? That's speed, right? Yeah. Exactly. Thanks. Good catch. Yeah, and yes, you're learning. Fantastic. Okay. So in layer 2, well, actually, let's talk of bandwidth again, speeds, right? Bandwidth and channels, right? Ethernet, you got 10 meg, 100 meg, gig, 10 gig, 100 gig, plus, 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 and goes beyond. In breaking that down into channels with T1 or T carriers, you've got that DS1, 1.544 megabits exactly, right? And that's the reason why is 24 DS0s. DS0 is a 64 kilobit channel and allows for 64,000 bits per second to travel over that one channel. And that's broken up using a time division multiplexing. It shares a time slot on that T1 carrier. When you add 24 of them together, you get 1.544 meg, okay, or 1.544 megabits of capacity. And that's your well, speed or bandwidth. I'd rather say bandwidth, and you're right. You caught me again, Brandon. In the ISDN world, which we consider PRIs and even BRIs, we haven't seen a BRI in ages, but where we've seen PRIs, we see them a lot, transitioning from ISDN PRIs to voice over IP. That's 23 DS0s per T1 carrier, and the reason why is that you have bearer channels and data channels, and again, that could be a course all on its own to discuss that. But in a straight T1, you've got 24 time slots. In a PRI, you've got 23 time slots that you can carry data, but it's clear channel. Okay, and again, I don't know if I want to get into explaining the differences, but with T1. Yeah, I might as well touch on it. You've got 24 channels to be able to communicate per channel, like channel 1 to channel 1 or channel 5 to channel 5. Something has to control that communication, and we use what they call least significant bit, and we take information out of that channel, 64 kilobit channel, and allow you to have 54 54 megabits, 54 kilobits of real data or bearer data, and the rest of it is used to signaling, okay, start and stop, and how clean is that data, error checking, that type of thing, is used to, so that they're not clear channel. You can't get a full 64 kilobit of data through on a T1 carrier. Whereas an ISDN PRI or ISDN connection, you can, because that data per DS0 is 64 kilobits clear, point to point, because we use channel 24, the highest channel, to actually do the signaling for all of the channels in that link. Okay, so the 23 channels are controlled by one channel. So all of that control channel or data channel is doing the control for all the bearer channels, which are the 23 that are left over. Okay, so in a T1, they're not clear channel. In an ISDN PRI, they are clear channel. Okay, there's no loss of that bandwidth point to point. Hope that makes sense. And then we multiply that configuration of PRIs or T1s into things like DS3s. Okay, it's a much bigger connection and allows for a much bigger pipe, or 44.7 megabits. 45 meg is traditionally what we call a T3, and essentially it's broken down into 20, and mathematically it breaks down exactly to 28 T1s. Okay, so 28 of these 1.544 megabit equals 44.746 megabits per second in a T3. Okay, and that's essentially what a T3. So DS3, don't let it scare you. It's just 28 T1s. That's all it is. Nothing, no big deal. Okay. Now, in layer 2, let's move up a layer in the OSI model. We move up to layer 2. This is where Ethernet becomes real. This is where Ethernet was invented. It was invented in layer 2. And frames inside Ethernet, point-to-point protocol or frame relay are all layer 2 protocols, okay? We're beyond the physical layer. We're now into a data link layer, or we're actually looking at the ones and zeros, and we're now framing that data to become Ethernet. So Ethernet lives in layer 2. And that's where it constructs the bits that are being sent into things like a header, okay, the payload itself and the trailer. So you get the beginning, the middle, and the end. Okay, that's the Ethernet. That's what Ethernet is responsible for, and a huge variableness in sizes depending on what protocol and what version of Ethernet you're running. But that's not really important. The important thing is that layer 2 is where Ethernet begins and lives, and this is where your switches live. Okay, they live in layer 2. Network interface cards, or NICs. Okay, that's your device on your laptop or your PC. Will plug a cable into a NIC card. Okay, bridges bridges and switches essentially do the same function, but it's a different name for the same sort of thing. And VLANs, okay, run in layer 2 as well. Okay, and they're a virtual LAN. This is where the word LAN, like local area network, comes into play, and they run on top of that. Inside that Ethernet frame, we can get VLAN tagging, which says we're on a virtual LAN. So instead of having a physical connection from one device to another, we're now doing it logically. And you'll hear me talking to network administrators in some of our meetings where we talk about a logical network and a physical network. And physical network is a point-to-point physical cable. If you want to run two separate communication links inside that cable, then we now have two logical networks inside a single physical network. Okay, and that's where that term comes from. So you have logical networking, which is VLANs, and physical networking, which is Ethernet. Okay, makes sense. Now, what the language that's spoken inside layer 2 is a hardware address or a MAC address, and that MAC address is universal around the world, and it's basically built up of 6 bytes of data. It's all hexadecimal, broken into this format. Okay, and you will always see it in the format, and it is done in hex. So it's valued from 0 to F, okay, or Fox. That's why you'll see letters and numbers. So it's essentially every digit, instead of being a decimal base 10, so from 0 to 9, which would be 10 possible changes, we now go from 0 to F as being the highest one, and that's 16 possible numbers. Okay, so if you have a base 16 as opposed to base 10, then we now have a much larger range of data that we can talk, and these are 6 bytes per MAC address. Now, like I say, when it's kind of evident here, I've broken in 2 halves. The reason why it's broken into 2 halves is a MAC address, which is kind of cool because you're looking for a piece of hardware on a network, and you know it's made by Polycom, or you know it's made by Cisco. The first 3 bytes, or the first 3 sections of a 48-bit address of a MAC address, those 3 bytes are the manufacturer. Okay, and they're universal. That's been fixed globally. And if you do a search for OUI codes or MAC address lookup on the internet, you can just do a Google search. You might want to write that down as well. Just do a Google search on MAC address lookup, and it will show you Polycom 00004 F2. Okay, this would be a 4 in this portion. So if you do a lookup for 0004 F2, that's Polycom. Okay, that identifies the manufacturer, Polycom. So the physical hardware of that network device is made by Polycom, and the last section is the individual or unique identifier for that piece of hardware. Now, it's not impossible, but it's rare that there's duplicates. Okay, duplicate MAC addresses around the world. That is very possible. It's not an infinite number. We do see it. I've seen maybe a half a dozen in my career where I've seen duplicate MAC addresses, but it's very rare. If they're on separate physical networks, makes no bearing at all. The only time they have issues is when they appear on the same layer 2 physical network. Okay, that's when they have problems, because then you have a conflict, right? If there's no conflict, there's no issue. The cool thing is you can do on your PC, if you open up your command line, try an IP config space /all. Okay, you will see a ton of information show up from your PC that shows you your hardware connection. That'll be your NIC card that I mentioned earlier, as well as your Wi-Fi adapter. You will see your MAC addresses associated, and they will be physically different because your NIC card might be manufactured by Intel, but your Wi-Fi might be Broadcom. Okay, might be a completely different Wi-Fi chip inside your machine. Okay, and they would have different physical MAC addresses right from the manufacturer code to the individual identifier. Okay, that's kind of a cool command to use, is ipconfig/all. MAC spoofing, yeah, absolutely, Adam. Yeah, MAC spoofing is used typically when there's any kind of authentication, and that's really what it comes down to, is authentication. Say you've got a real world situation where a customer has just purchased a connection from their ISP, and they supply the ISP or the internet service provider provides the router. Okay. And you want to use your router. You love your router, right? You don't want to use anything else. You don't want to use the ISP's router because it's a piece of crap. You want to use a real routing engine. And to be able to use your device, you have to make it look to the network that you're connecting to that you're actually using the one that was supplied to you. Okay, and let's use this number as an example. So the customer was given a router by whatever the ISP is. This doesn't apply to TELUS, but you would have a MAC address, okay, a physical address that the router's interface is equivalent to. Okay, so that's the physical, call it a name, the physical name that was given to that physical device, and it's unique to that device. But you want to use yours. Okay, you want to bring in your hired gun to be able to take that place. The only way you can do that without calling up the ISP and saying, I have a different device, here's my new MAC address. You can make it seamless by doing MAC spoofing, and you tell the network card on your router to change its MAC address to be equal to what you had before. Okay, and you can use MAC spoofing to get around that issue, and it's all to do with authentication, because the ISP is looking for only its physical devices to be able to connect to its network. Okay, it prevents rogue connections essentially, but anybody with any kind of networking skill can do MAC spoofing, and boom, they're connected. Okay, there's still other authentication layers, farther up the OSI model, but that's the first one you'll see is MAC layer, and you'll see that as well in other pieces of software or protocols that we use in the VoIP world. LLDP is one, link layer discovery protocol, or CDP, which is Cisco destination protocol, I think, or device protocol, and it's Cisco proprietary. CDP and LLDP are based on MAC addresses, and they will respond accordingly. And yes, you can spoof addresses on it to make a PC look like a Cisco phone, or make a PC look like a Polycom phone, and it will assign a VLAN and an IP address that's completely different because you've changed that MAC address, and you can do that on a PC. You can do MAC spoofing. So yeah, great question, Adam. Thank you. Layer 3. This is the kind of where the rubber meets the road. It's where the packets get identification. They get a name of where they're supposed to go, or where they came from. That's your source, your destination, and now we're talking packets instead of frames. So in layer 2, as referred to, we're talking about frames. Okay, it's frames of Ethernet in layer 2. In layer 3, now we're talking packets, because we're doing encapsulation. We're taking packets and putting them inside frames. Okay, we're taking that address information and sticking it on the outside of an envelope. Okay, and routers, layer 3 switches, they all do layer 3. Layer 3 is where IP address version 4 or IP version 4 exists. IPv6 exists here as well. And there could be a whole another course just on IP addressing, and maybe if there's enough interest, we can get into that at a later date as well. I could probably put something together for everybody on the line. IP v4 is typical worldwide. It has been for decades. Yeah, that's long. Yeah, a couple of decades, anyways, 20 years. And it's based on 32 bits, 4 decimal octets. So if you look at the bits that we're looking at here, there's 4 sections or 4 octets, 205.169.85.218, okay? Or if it's a local address or non-routable, this is an RFC standard. There's different classes of it, and I'll go into that a little later. 192.168.1.2, okay, is another IP address, and these are 4 octets, okay? So when I say what's your second octet, that would be .168. What's your 4th octet? .2, okay? It's a logical explanation of what these numbers mean. Don't be confused with you know, trying to count addressing and make an assumption that they're sequential, numerically sequential. They're not. And I'll kind of get into that because these are binary representations of a given value, okay, or a value represented in binary that's been translated into a numerical value. Sounds complicated, but not really. When it comes to machines, they can only talk ones and zeros, and that's why IP addresses, you know, a lot of times mystify a lot of people. But if you really think about it, it's just a representation of ones and zeros. If you broke this down into ones and zeros, it would make a whole bunch of sense. It would be just a nightmare to manage. You know, what's your IP address? Well, it's 1101011.01101011.0101101 .1111101.0. Can anybody repeat that? You know what I mean? That's why we've got, you know, a numerical version, because humans can understand it better, and that's really the reason why it's kind of a weird kind of seems arbitrary, but it's not. IP address version 6, it's a huge expansion of version 4, and maybe I'll back up a little bit too, a little bit of history on IP version 4. A couple of years back, about 5 years ago, there was a big panic on the internet. We're running out of IPv4. Yeah, we're running out of IPv4. But with the addition of IPv6 and what we call supernetting, a lot of that IP address space, and a lot of it was unused. I mean, an enormous amount of IPv4 was unused. And, you know, it was sent back to, in North America, we use ARIN, which is American Registry of Internet Numbers. ARIN now has a surplus, well, not a surplus, but they have a quantity of IPv4. You can still go out and buy IPv4 address if you want a /24, you know, or a subnet of your own. You can buy that from ARIN. No problem at all. There's addresses available. So as long as we manage it correctly, and there was a lot of waste and misuse of IPv4 when it first came out. You know, a lot of people said, "Well, I want a full Class A for myself." Well, it was enormous waste, and I'll go into different classes in a little bit. But now that we've kind of, you know, shaken the tree and said, "Hey, are you really using that?" You know, it's brought that number down. So there's no real shortage. There is a shortage, but it's not the end of the world. IPv6 has allowed for the expansion of the internet essentially to go unencumbered completely. Okay, and one of the descriptions of the quantity of IP addresses available now is that every known star that we can see in the known universe, we can give an individual IPv6 address to and not run out. Think about that. That's huge. Okay, it's absolutely huge, the number of IP addresses that are available through IPv6. And there's no way we can exhaust them all. We will always have those. Now, layer 4, this is where we talk TCP. Let's move up a layer in the stack. And in layer 4, this is where the datagrams for TCP exist, and UDP, so Transmission Control Protocol, User Datagram Protocol, SSL, which is our security side, TLS, Transmission Layer Security, or RTP, Real-Time Protocol. All of those different protocols, we're now talking datagrams. Now you notice that we've gone from, let me back up and review a little bit, we've gone from frames in layer 2 to packets in layer 3. And now we're talking datagrams, okay, in layer 4. Okay, You don't have to remember that, but it's just a different designation. So now we're talking datagrams, and datagrams is where the payload exists. RTP carries the payload. That's the real-time protocol. You'll probably know that voice over IP is an RTP protocol, voice over IP, and that payload, and we use sequence numbers to track it, to be able to make sure that they get at the other end, and they're the sequence numbers equal at both ends, so we know what piece of data we're talking about. Port addresses in layer 4, instead of an IP address, now we have a port address, and this is where ports come in. Port 80. Anybody know what port 80 is? Probably a few hands going up. That's HTTP. That's the World Wide Web. Port 21. Common port. Yes, perfect. Thank you, Adam. Is FTP, and we have a number of ports out there. 443. That's another one. Anybody know what that one is? 443. Yeah, beautiful. SSL. That is the secure HTTPS is what we'll see when we talk about a device that connects to the to our registration servers. It has to be encrypted. Okay, and that's one of the reasons why I get a lot of questions on, is this phone compatible, with Business Connect? And I'll say, well, how old is it? Does it support HTTPS for provisioning? It's an older Polycom phone, and it's a rev out of existence that has old firmware, and it doesn't support HTTPS. Well, then no, we can't use it. Okay, because we have to support HTTPS or secure provisioning, and that uses a specific communication on port 443. Okay. And then there's things like registered ports. Registered ports, run from 1,000, and these aren't fixed values. Actually, you can use any port you want, but it's kind of a agreed upon standard is what the port addressing, and you can Google, port numbers, and it will list so many different types of ports, especially registered and well-known ports that are somewhat of a, they're kind of fixed value. It's the best way to describe it is it's chiseled in the ice, okay, or scribed in the ice. It's not permanent, and you can change it at any time. You can run an HTTP connection, a web connection, on any port you want. It doesn't have to be port 80. It's just that's the port that is the most common port, and assumptions are made from a communication standpoint that you're going to communicate at port 80. But you can use 8080 or 8,000 or 5,000 or 22,000 or whatever number you want, as long as both ends agree to that layer 4 port address. And that's why we, in the VoIP world, have given ports or fixed ports, registered ports that we use for SIP communication, because they're common throughout the world, and everybody treats them a little differently. So when it comes to things like QoS, we want to make sure that communication happens at a particular port level, and the connection actually will go through and be registered at the far end, and acknowledged at the far end. And then we jump into the dynamic or private port numbers. Those are the really high port numbers, and these port numbers can change, at a whim. Okay, they're dynamic, they're and considered private, but there is a finite number of ports that can be used. 65,535 is what we have available to us in layer 4. Now we move up to the session layer in layer 5. Again, some of these layers can be skipped depending on what the data is. If there's no need for RTP, maybe session 5, layer 5 is skipped for data communication. But in the session layer, it's going to have that transport protocol, RTP, for example, have that payload tracked by the sequence numbers in layer 5. Okay, not a lot to talk about in the session layer. Presentation layer has a little more reliance on what's above it from the application layer in layer 7, and it's what they call data representation, and how we represent that data to the application layer. And I mentioned EBCDIC, that's EBCDIC, or if I can remember exactly what it stands for, and I've drawn a blank at the moment, but it's enhanced binary code. Okay, I've gone completely blank. I should have had it written down, but it's an older term, but it's used to this day. Has to be. ASCII is what we commonly, extended binary coded decimal interchange code. Thank you very much, Adam. And Adam probably Googled that or knew it as well. But yeah, it's EBCDIC is something that's used exclusively in layer 6, transcoding, for example, to Unicode or representing Unicode or ASCII. ASCII is what we use in everyday world, is our alphabet, our numbers. Okay, 128 bits can represent any number on our keyboard, for example, as an ASCII code, and numbering schemes as far as representation goes. Data compression. Data compression is also at layer 6. Things like MPEG, JPEG, G.729, 722, 711, all of those different protocols or codecs, I should say, are part of that presentation layer, and that allows for the world or the internet as we know it today. Without layer 6, we'd be still stuck at doing very basic functions, sending email or having a point-to-point text conversation. The advent of things like codecs and data compression has allowed us to push video, audio, pictures, voice in extremely little bandwidth and very little data requirement to get point to point to get us that quality image or that quality sound or just having a voice communication. And the last thing in layer 6 is data security. When it comes to key encryption, we get symmetrical and asymmetrical, and I won't go into that. That's another course all on its own, and I'm not a data expert, so I'm not going to be able to address that 100%. But that's where our private and public keys are represented inside the layer. And moving on to the last layer, which is layer 7, the application layer. This is where the user resides, or the application sits, and this is where we actually get the the end product, whether it's input or it's output. That's where we talk. Layer 7 will be using the port number from layer 4. And pointing that communication string directly to the application, for example, on layer 7. Okay, and it's very, very common for this to happen, and skipping layers 5 and 6, and that's probably the best example of that. Okay, Q&A for the QSI model, and I'll open up the mics if we have any questions at all. Somebody sounds like we've got a noisy background in the back there. Okay, I'll just I'll mute it back there. And okay, so where we started at the beginning, where do we stand? And you know what? I think we're going to be giving you guys back some time today, because we're at the near the end of part 1, which is great. I know in a classroom situation, I would have easily pushed this to 2 more hours, just with interaction and chatting and being able to discuss more of this topic. But on a web presentation, it's a lot easier to go through a little faster. It is being recorded, by the way, so anybody that's on this will get a link to the recording, and you'll be able to review it at any particular time. So let's go through that last question. Where do we stand? So anybody want to pop on the group chat? How's your knowledge now on data? From going from not knowing anything at a 0 to being able to do subnetting and super subnetting. Would you be able to do that? Fantastic. And Yeah, and hey Brandon, I can take that offline with you. He's asking what courses or certificates do I recommend. There are a number of them that are out there that are non-TELUS, non-Business Connect, non-VoIP specific, just data courses. And to be honest with you, there are a ton just on YouTube that you can listen to. You can learn a lot by taking just a topic of interest, IP networking, security, things like that, and just do a search on YouTube. There's a ton of information out there that can be learned upon. But if you're looking for something as a real certificate, yeah, there's lots of courses out there that you can pay for and get certified on. They're typically instructor-led, reinforcement. Yeah, the CCNA is a great way to start. It's somewhat Cisco centric. I've done the CCNA course. I've done the CCNP course. I'm not really impressed with the amount of Cisco content. I'd rather see it rather Cisco agnostic, just network related. But the one course that Cisco did was an IP boot camp that was phenomenal because it was not related to Cisco at all, even though Cisco did that course. I don't know where it would be now or where it is, but that's a great a great way to start any of the boot camp courses because it goes through a lot of this and integrate a lot more detail. They're typically a 5-day course, and you really gotta take a lot of notes. You get a lot of material out of them too, and you could do a ton of IP networking, IP subnetting, designing networks. Because if you understand the basics, you excuse me, you can design a network pretty quickly. Just with a few pointers, but yeah, CCNA is a good start. It can be an expensive course though, so it depends. But yeah, you could use Patrick's credit card number, yeah, for sure, if you needed to. Let's see, Patrick and Paul, anything to add on your side?
No, I think the course was great, Doug. There's it was like drinking through a fire hose. To be honest, there's lots going on. So I'm glad it's recorded so people can review it at a later date. That's great.
And I've got it recorded, and I will do a. Let me see. Let me just stop the recording now so it doesn't eat up